In the late 1950s, the first satellite was launched into space. Now, about 70 years later, entire industries have been built up around using these satellites to navigate. But how does your phone know where you are when you're driving? And how do we use these satellites in aviation? Let's find out. Hi, I'm Grant and welcome to Class 12 in the Radio Navigation series. Today we're going to be having a look at satellite navigation. Satellite navigation is very useful because it allows us to navigate to areas that are very remote and might not have any ground-based navigational aids, but it does have a few drawbacks too. We refer to satellite navigation systems in day-to-day life as Global Positioning System, or the GPS system. GPS is, however, just one of 4 global satellite navigation systems. The others are the Russian GLONASS, the European Galileo system, and the Chinese Beidou system. They all function using essentially the same concept, so we'll first focus on the most established American-based GPS, and then have a quick look at the differences of the other systems. So GPS was initially developed by the US military to give highly accurate tracking information for launching missiles and that sort of thing in the 70s. Then they started allowing civilian use of the system in the late 80s and the early 90s with a reduced level of accuracy. The system consists of 3 parts. There's the space segment, which is all the stuff out in space. It's the satellites in orbit forming a constellation of satellites around the Earth. Then you have the control segment, which is a system of ground-based antennas and sort of satellite dishes that are monitoring the system for integrity and correcting any flaws in the system. Then you have the user system. This is your phone, computer, smartwatch, or in our case, the aircraft. The space segment of GPS consists of a notional constellation of 24 satellites. Notional meaning the minimum to make the system work. These satellites orbit the Earth at 20,200 kilometers in the sky, which means that it orbits every 12 hours around the Earth. And it does so in 6 different orbital planes, each at 55 degrees to the equator, but spaced out evenly around the equator, creating a large amount of overlap and crossover. This interlocking web of satellites means that at any one time, anywhere on Earth, there should be between 5 and 8 visible satellites. I've tried to represent this just from one side. You've got the 55-degree angle with a few orbits going around it, but if you imagine that repeated on the other side or at like 90-degree turn, you would get that there's a lot of crossover of these orbital planes. The satellites transmit on 2 frequencies in the UHF band. You've got 157.42 megahertz and 1227.6 megahertz, which are both used by the US military to get accurate position information in 3D space, called the Precise Positioning Service. The downgraded civilian version only uses the first of these frequencies, which is known as the L1 frequency, for very boring reasons to do with how radio waves are classified in the US military, but this 157.42 is the L1 frequency. This allows for less accurate standard positioning service to be used in all sorts of things, from food delivery apps to landing a passenger jet in bad weather. The L1 frequency transmits from the satellite with 2 pieces of information. The first is known as the course acquisition signal, consisting of an identifier code and timing information. This is a long string of digitally modulated information so the receiver knows which satellite the signal is coming from. It is so long that it can look just like a random string of information, which is why it is called a pseudo-random noise code. It looks like random noise, but it's not actually, it's pseudo. In this PRN code, some information on the time signal, time the signal was sent, is included. This is measured from 4 highly accurate atomic clocks within the satellite. The time the signal was sent is compared to the time it was received, and using speed distance time calculations, a distance from the satellite can be calculated. The issue with this is something similar to what we see in DME measurements. For example, if we just think of this as some DMEs for now, if we know we are 20 nautical miles away from a DME station, we don't necessarily know the direction. We get a circular ring of range. We've got a range ring. If we add in another DME, we can draw another range ring and narrow it down to 2 points on those range rings where they cross over. If we add in a third DME range ring, we can get a more accurate location still. This is the same principle that is used for satellite navigation, except that the range rings are actually range spheres, and they're three-dimensional. So we basically need to get multiple points of intersection to get an accurate picture of where we are. We need a minimum of 3 to get an accurate 2D location, just like in DME, and we need 4 satellites to get an altitude element to make it a 3D position fix. Seeing as that anytime GPS is available, it has 5 to 8 satellites visible from any point on Earth, we can get a pretty accurate 3D position fix at all times from most locations on the Earth. It's also important to note that this position is assuming a certain model of the Earth, which is called the WGS84 ellipsoid. This is basically a standard diagram of the Earth that all GPS systems and receivers use to plot their position on, and it means that all GPS receivers are using basically the same map to plot on. So that's the first part of the signal sent. The second part of the signal sent by the satellite is known as the nav signal, which is sent out of the satellite in little chunks of information every 30 seconds. And this packet of data takes about 12.5 minutes to download and contains data on the satellite system and is downloaded periodically by the receiver to make sure it has the most accurate information of satellite positions and other things. It consists of the almanac message, which is a rough estimate of the expected satellite positions for the time of day, valid for about 180 days. Then you have the ephemeris data. This is more accurate information on that specific satellite which is sending the message, which is valid for about 4 hours, and it's used for fixing a more accurate position. Then you have the satellite clock correction. This is a small correction that might be needed to correct small inaccuracies in the atomic clocks, which are picked up through the control segment, through the monitoring segment down on Earth, and the corrections are sent back by that monitoring segment to tell the satellite clock that you have to give a correction when you give your timing details as well. Then you have a UTC correction, which is a similar thing. It's a correction applied by the user segment that converts UTC time, UTC being basically the standardized time on Earth, and it corrects that for GPS time. It sort of converts one between the other. The difference between GPS time and UTC time is that UTC time has leap years and leap seconds, etc., whereas GPS does not. So there has to be a slight adjustment made for that. Then you have an ionospheric model that's sent down as well. This is a model of the ionosphere, which can affect the signal strength and accuracy. So the results can be edited according to this model so that the atmospheric and ionospheric effects are counteracted as much as possible. Then you have the health status. It's a basic message that says this satellite's good for use or this satellite's not good for use. If you get one that says it's not good for use because it might be offline for maintenance or something like that, then the user segment should know to ignore the signals from that satellite. The control segment is essentially the bit behind the scenes that makes the whole system work. It consists of multiple ground antennas that are monitoring the status of the constellation and individual satellites. These ground antennas can monitor the atomic clocks on board each satellite and calculate the corrections based off of a master clock. The master clock and station is based in California, and this can then send out those timing corrections that are calculated by each of these individual substations, and it can also send updates to the databases and basically send the latest nav message that has to be sent to the satellites in order to then be downloaded by the receivers and the user segment. The control segment can also consist of some ground-based augmentation systems, which we're going to have a look at in the next class. The user segment is your phone, computer, or aircraft. The user segment is the place where the calculations in terms of position are actually being performed. The aircraft will receive the signals from the satellites and compare them to its own internal clock, and along with the nav portion of the signal, from the satellites, it can determine the position of the aircraft on the WGS 84 ellipsoid very accurately. Depending on the phase of flight, the accuracy of the GPS signals is required to be higher or lower. Higher when close to airports and the ground, lower when over the ocean and not near anything. This is something called performance-based navigation, which we'll look at in a couple of classes' time. Anyway, most modern user receivers, even in small planes, are multi-channel, meaning they can pick up signals from multiple sources, even from different constellations, with an aerial on top of the aircraft that is fully exposed to the sky above. This generally means that a modern receiver can pick up all satellites in view, and in view means that a satellite is above the horizon by about 5 to 15 degrees. It isn't visible before this due to high levels of atmospheric and ionospheric disruption. Might be visible, but not really usable, I suppose would be the better definition. The angle where you aren't able to use the satellites is called the mask angle. And old receivers would have a very low mask angle to try and sort of widen out their view as much as possible. Because back in the day, any signal was a good signal. Now though, there's loads of satellites up there in different constellations, so the signals from just over the horizon can be ignored, which means that the mask angle can be higher because it's compared to the horizon, which kind of narrows the view, but it does mean that you're only getting the most reliable signals, and the ones that are affected by that ionospheric and atmospheric disruption can be ignored, or not received, and a more accurate position can be determined from that. So there are a few errors in the GPS system, which are listed out here. We'll just go through them one by one. So the first one is ionospheric propagation delay. This is interference from the density of the ionosphere and atmospheric conditions like moisture and clouds, and this can cause a delay to the transmission time that it takes for the signal to reach from space to the receiver. The more the signal has to travel through the ionosphere and atmosphere, the more the signal is delayed, which means we get the best signals directly overhead. And this is basically what I was just talking about. We adjust the mask angle, which will allow only those signals that haven't traveled through that much of the atmosphere to reach us. Pseudo ranges are where we have an incorrect range calculation because of the accuracy of the clocks. So satellites use extremely precise atomic clocks, whereas the clock in the receiver is unlikely to be an atomic clock. This means that there might be a slight error in timing, and therefore the distance calculated from the satellite might be wrong, and therefore the position might be wrong as well. The solution is quite simple though. The receiver applies a small correction in the timing, sees if the area of uncertainty in position has reduced, and if it has, another correction is applied, and so on in an iterative way, repeating and trying again and again to try and reduce that area of uncertainty. So orbital variations are basically the orbit isn't what you predict. The nav message containing the almanac and ephemeris information might be slightly off if the satellite has been changed from the predicted orbit. This can be caused by solar winds, gravitational effects of the sun, earth and moon, and when this happens, any error by 0.5 meters or so is considered too great, and the satellite will be taken offline by the control segment monitoring to fix that sort of thing. When we send, it'll then send a new correction to that nav message, to the ephemeris data, which is uploaded to the satellite for use once again by the user segment. Instrument errors are the error caused by the receiver, and it could be interrupted by electrical background waves, computational errors, dodgy hardware or software, and basically the better the equipment, the less likely these instrument errors are to occur. Multipath errors are when secondary signals are basically bounced off and reflected off terrain, and therefore takes slightly longer to reach the receiver. This can lead to confusion in position because the timing's all off and therefore the distance would be off. And it's generally only an issue at low levels where the signal might be able to bounce off terrain first before reaching the antenna. Up high above the terrain, this error isn't really an issue. So atomic clock error is basically an error in the clocks. So the atomic clocks, whilst extremely accurate, can sometimes have little errors in them. The error in the atomic clocks is only detectable by comparing it to the master atomic clock in California, and it's only this master station that can send the corrections in timing to these satellite clocks in part of that nav message that we saw earlier. And this means that because it's only the California-based satellite dish or the ground antenna that can actually send this correction, it means that the clock might not be able to be corrected for a long while. If the satellite's overhead Japan, for instance, it's going to have to travel all the way across the Pacific until it's near about the ground station in California before the correction can be applied. Dilution of precision is a geometric effect, really. If we use ranges from different sources to create a fix in our position, if the satellites are all very close together, then we get a large area where the position can be in. It's just a geometric phenomenon, which is why it's sometimes called geometric dilution of precision. So what you want for the optimum geometry is for them to be separated by 120 degrees, so 3 each to be separated by 120 degrees, with the fourth directly overhead, and this reduces the area we can be in to the ideal size and increases the position accuracy. Jamming or spoofing aren't exactly errors of the system as such, but they are more deliberate sabotaging of the system. This is common around war zones, for instance, where one side tries to stop the other from using GPS or GNSS, Global Navigational Satellite Systems. This happens to me a lot when flying near the Middle East with all the tension and wars going over there, and it's quite common to have GPS signals jammed where they're completely blocked, or spoofed where they're deliberately modified. So a spoofing bit of equipment, I don't even know what you call it, a spoofing computer, basically absorbs the signal, applies a slight time delay, and then sends that to the aircraft, which means that the position isn't accurate. And they can do that highly accurately to make you think that you are flying somewhere else. The other day I was flying out of Cyprus, and on flight radar it said that I'd taken off from Beirut, which is not Cyprus. So it's a slight modification because of the spoofing, and the flight radar was showing that we'd taken off from Beirut, which was completely wrong. But the solution to this is quite simple. You just don't use GPS. You just use DME, VOR, NDBs even to navigate using standard methods where you don't have the possibility for signal interruption. All these other systems use the same principle of timing to find out distance, and multiple spheres of distance intersecting, that's your position. I'm just going to run through these quickly. So GLONASS is the Russian GPS, works using the same principle, timing, distance calculations from multiple satellites, consists of a satellite constellation of 24. They're in 3 orbital planes, each at 65 degrees to the equator and at an altitude of 19,100 kilometers. This means that they orbit the Earth slightly faster, about 1 time every 11 hours, 50 minutes. And this system allows for at least 5 satellites to be visible from any point on the Earth at any time. Many regular satellite navigation systems like your phone or computer can use these satellites as well as any of the others. In aviation though, the accuracy of the system can't be guaranteed. So in Europe at least, the system cannot be used by aircraft. Galileo is the European version. Functions the same as GLONASS and GPS with a constellation of 27 satellites with 3 spares in orbit waiting to fill any gaps that if a satellite breaks or has to have some maintenance done to it, then one of the 3s will jump in and fill in the gaps. They orbit in 3 orbital planes at 56 degrees to the equator at an altitude of 23,222 kilometers, which means that they orbit the Earth once every 14 hours. Then you've got the Chinese Beidou system. It uses a constellation of 30 satellites in 3 orbits, but not equally spread over those orbits. It's 3 different types of orbit. Some orbit in a geostationary orbit, which means that they don't move from that position over the Earth. You put a satellite over Beijing and it rotates at the same rate as the Earth is rotating, so it looks like it's floating directly overhead Beijing, for example. There's also some ones, some orbits that rotate the Earth at different rates. So there's quite a weird mashup of geostationary and orbiting satellites. It basically means they get a very good view of the Asia Pacific and China region, and maybe not such a good view of the rest of the world. But what this means is that they've got good satellite positioning navigation system for their own backyard, which is what they want. And it's still not fully released what all the details are without traipsing through a million different articles and things like that, because it is Chinese, it's behind that great firewall. So what I've been able to gather is this. It might not be completely accurate, but this is just from a few different articles I've read. We've got orbits from 21,000 kilometers to 36,000 kilometers. 36,000 kilometers is going to be the geostationary orbits, which means that it rotates the Earth once every 24 hours at the same time as the Earth is rotating. And 21,000 kilometers would mean about 12 and a half hours for some of those other orbits. So a quick summary then, we got the global navigation satellite systems. There's GPS, GLONASS, Galileo, and BeiDou. GPS has 24 satellites at 20,200 kilometers up above the Earth's surface. 6 orbits, each at 55 degrees to the equator, and it takes about 12 hours to orbit. GLONASS, Galileo, BeiDou, slightly different. I just talked about them. Go back and look if you want to know the details about them. GPS transmits on 2 frequencies. You've got the 12227.6, which is military only. Then you've got 1575.42, which is known as the L1 frequency, which is what we use to help us navigate as a generic non-military person. It consists of 3 segments. You've got the space segment, which is the satellites orbiting in their constellations and orbits. You've got the control segment, which monitors everything, applies any corrections or calculates any corrections, then sends them off to the satellites. Then you get the user, which is us, which is where all the calculations on position actually take place based off of speed, distance, time. You get those range spheres, which all interlock, and we can calculate a pretty accurate position, which is on the WGS 84 ellipsoid, not the actual Earth. So in that L1 message, there's 2 components. We've got the PRN code, the pseudo-random noise code, or the coarse acquisition code. It has an ID of the satellite and the time. We need 4 for an accurate 3D fix, because we need 3 for the 2D and then a 4th one, ideally directly overhead, to give us the altitude information. The second part of the signal is the nav signal. We need to know where these satellites are in order to get the time and distance from them and calculate where we are on the WGS 84, I was going to say on the Earth, but technically the WGS 84 ellipsoid. Anyway, nav signal contains the almanac, which is a database of where all the satellites are, valid for about 180 days and obviously updated every 180 days. The ephemeris data, which is a more accurate position of where that satellite is, updated every 4 hours or so. It might contain any satellite clock corrections, which are basically any errors in the clocks which are detected by the control segment and sent out by that master station back to the satellite. You've got a UTC correction. Satellite time and UTC time are slightly different. UTC has leap hours and seconds and stuff like that. Leap hours? Leap years and leap seconds and things like that, whereas GPS time doesn't. So there's a slight conversion that has to take place. You've got the ionospheric model, which is a model of the atmospheric and ionospheric conditions that might impact the time it takes for the signal to reach Earth, and corrections can be applied based off of this model. Then you get the health status, which basically says good to go or don't use me. Simple as that. Errors in the system. You've got the ionospheric propagation delay, which is the more ionosphere it travels through, the more likely it is to get delayed, and the signal accuracy and position accuracy is likely to be less accurate. This can be solved slightly by using a mask angle. Mask angle is the amount of the angle from the horizon that you don't want to pick up signals in. So it was 5 to 15 degrees because they wanted as much satellites, as many satellites as possible to get their position back in the day. Nowadays though, you can kind of discount the ones that aren't going to be accurate because there's so many satellites up there. So they've increased the mask angle, which means that the view is a bit narrower, but only the good signals without ionospheric propagation delay are being detected. You get pseudo ranges, which is basically a difference in the accuracy of the clocks. You get atomic clocks on the satellites and most likely not atomic clocks on the user segment receivers. And that small inaccuracy in the timings and the accuracy of the timings can lead to a large calculation of distance error. But what happens is a small correction is applied. If the error gets bigger, they go, oh no, we'll go the other way. Let's correct it the other way. And if the error starts to reduce and the area of uncertainty reduces, then you know you're going the right way and it corrects according to that. Orbital variations are caused by wind, gravity, things like that, and wind, solar wind, not actual wind, solar wind or gravity. And it basically means that the orbit that is planned in the almanac or ephemeris isn't the orbit that is actually happening. So this can be monitored by the control segment and new updates to the ephemeris data added, corrected for that. Instrument error is software, hardware of the receiver. Multipath is it bounces off a hill or a mountain before hitting you, obviously taking a bit longer, means the distance isn't going to be accurate. Atomic clock error is what the control segment is monitoring a lot of the time. Atomic clocks can drift, so it's just basically monitoring that drift, and it can give out satellite clock correction information based on any drifting that's happening. Dilution of precision is a geometric effect. Basically, if they're all 3 or 4 satellites that you're using are very close together, you're going to get a large area of uncertainty, whereas if they're nice and spread out, cutting each other at good angles, then the area is a lot smaller. Then you got jamming or spoofing. Jamming is when the signal is completely blocked and you don't get any position at all from GPS, no reliable information at all, whereas spoofing is when it is modified to give false information to you. Spoofing is quite hard to detect unless it's very obvious, but spoofing could be as subtle as sending you 2 miles off course or something like that. So spoofing can be quite dangerous. Jamming, you know it's happening, so it's quite easy to spot.